I'm sure Dr. Schwann did this, but N-amines are cool and amines are cool in biological systems. And later on, I'll be talking about aminamines again, and specifically in the Mannich reaction. The way I recognize N-amines, particularly in biological systems, they become my carbon nucleophile, whereas amines become my carbon electrophile. So we often see N-amines being used as nucleophiles, but amines or aminamines are often used as carbon electrophiles. And the reason for this, the reason it's applicable to biological systems, you don't have the luxury of using really, really strong acids in a biological system. So N-amines and amines are often formed from protein structures as intermediates. Specifically, it often uses the amino acid lysine. So for those of you that will continue on in biochemistry, it's kind of cool. It's kind of a, I like to talk about these systems because, again, when you take biochemistry, I want you to remember that N-amines are always formed in a lot of systems, and they really become our carbon nucleophile. Okay? And so recognize, even I don't have it here, but all of you guys at this point should be able to do a resonance structure for this guy here. So if I push this nitrogen electron here and push it onto carbon, notice that generates a resonance structure in which I have a nitrogen double bond here, so that nitrogen is positive, and I have a carbon that's negative. Now, obviously, that's not the important resonance structure. The best resonance structure is this one because it's neutral. But one of the things I always teach in the first semester when I teach resonance is there's two reasons for me to teach resonance. One reason is resonance is always a stabilizing interaction. So the fact that we have these really relatively acidic protons because the carbanion can be stabilized by resonance. But the second reason I teach resonance is resonance often tells me something about chemical reactivity. So it's very hard for me to see the resonance structure for this species, okay? So if you like, let me just go back to the document camera because it seems to be working. It didn't freeze this time, right?
No.
All right, let me just stop sharing for a moment. And you guys see the document camera?
Yes.
Yep. Okay, so what I'm really specifically talking about here is this N-amine. I'm just going to draw anyone because I can't recall what I had. Okay. As I pointed out, this is the best resonance. This is the best resonance structure because none of these atoms have a charge. And the way I teach organic chemistry, charges in general cost energy. Molecules that are neutral are always happy. However, sometimes the bad resonance structure, or not the bad resonance structure, but the resonance structure that is least contributing to the overall resonance hybrid is the one that we often think about with regards to chemical reactivity. So if I push this electron here and push it here, the resulting resonance structure tells me that N-amines are indeed nucleophilic. Okay, so the result of this is I have a positive here, and I'm just going to point this out that I have this electron pair there that has a negative charge. And because of this resonance structure here, this makes that carbon nucleophilic. Okay, so the idea here is that we're going to use N-amines and see if N-amines can function as a carbon nucleophile. Okay, you probably saw that in the Stark reaction that I believe Dr. Schwann shared. He taught that to you, and we talked about that. Okay, so again, that's what I'm really referring to here. So I want you guys to think about N-amines because of this resonance structure. That carbon is often nucleophilic. Okay, and it's often in biological systems, that's often used to make carbon nucleophiles. We don't have the luxury of using hydroxide. We don't have the luxury of using sodium methoxide. But in protein structures, this is what we're really employing. So,
Professor, can you show the bottom of the page real quick? Thank you.
Okay, I'm gonna stop screen share. I'm gonna go to my PowerPoint. Okay.
Okay.
Okay. So as you can see here, Enamines also react with Michael acceptors. And again, since enamines are not grignards, they're not organolithium compounds, they're not hydrides, we expect them to react at the beta carbon. Okay? So if I push the arrows here and that, and again, if you first like to show the resin structure that I drew for you on the document camera, you know, where you have the carbon with a double bond here, carbon with the electron pair, and this has a double bond. That can also be, you could use that resin structure to show directly that this guy attacks this to generate this species. Okay, so notice what I have here is I have an enolate, okay, that's formed, and I also have an iminiamine, okay, and so you should have learned a lot about iminiamines and with Dr. Schwann. The next thing I do is I'm going to protonate the enolate to make the aldehyde. Okay, so now I have an aldehyde that is attached to a 6-member ring in which I have a double bond to nitrogen of this 5-member ring. And if you really think about this double bond to nitrogen, this is iminiamine. Recognize you learned how to react you learned how to form iminiamines. Yesterday I talked about microscopic reversibility. And I stated to you guys, if you know how the mechanism of taking a ketone or an aldehyde and making an iminiamine or an imine, you know the reverse reaction. So don't forget this, please, that if you treat an iminiamine anytime with acid and water, you will remove this and reform the ketone or carbonyl system. Okay? So in the end, I'm able to form this type of system that is both an aldehyde and ketone. This is alpha, beta, gamma, delta. This is a delta ketyl aldehyde. Okay, so again, it's just an example that enamines will also do conjugate addition.
Can we take a quick break?
Yeah, what time is it? Yeah, please take a few minute break.